Alright, we're going to be trying to find any points of discontinuity, if there is any points of discontinuity. But the first thing we're going to look at is something real simple here. This is a polynomial function. X to the fourth plus 2x squared plus 1. Alright, so here's its graph. And of course it's always good to look at these graphs if you don't when you're first learning any of these kind of things. But now there's a property about polynomial functions, and that is they're continuous between negative infinity and positive infinity. So there is no points of discontinuity. In other words, there's no holes in this graph. The graph's not broken. Even though I'm only showing it from like -4 to, I don't know, 3 here. But the domain of this function is from negative infinity to positive infinity, and there are no points of discontinuity. Let's take a look at another one. Alright, so we've got the function f of x is equal to the square root of x, and we're looking for points of discontinuity. Now we've got to remember that the domain of this function is from 0 to infinity. Right, so we can plug 0 in and any number right to the right of 0 on the number line all the way up to well, infinity. But this graph here, don't let this mislead you here. These are just imaginary numbers here, but just pretend this doesn't even exist. Okay. Now this function here doesn't have any discontinuities because it is continuous between 0 and infinity, positive infinity. Alright. Okay, let's look at this function here. We have f of x equal to x squared minus 1 over x plus 1. Now I will tell you that if you plug -1 into the denominator, we are going to get 0. So that means that this is a possibility that there is a discontinuity in this function. If we factor the numerator, we get x minus 1 and x plus 1, and then we get an x plus 1 down here in the denominator. So this tells us, because we have an x plus 1 in the numerator and an x plus 1 in the denominator, that there is a hole in the graph. And so the first thing, remember, that we want to check is we're going to check the limit as x approaches -1 of x squared minus 1 over x plus 1, and I'm claiming that it's equal to -2. Now remember, we're using this -1 here because if we plug -1 into the denominator, we get 0. And of course, if we plugged it into the numerator here, we'd also get 0, 0 over 0. Okay, so we checked that first property. Now, in order to check this, remember, we factored it, canceled terms out, we got a new limit, but our new limit, remember, is still equal to our original limit. And so we're left with x minus 1, so you take -1, plug it in, and you get -2. Now I'm going to consider that you've got some familiarity here with solving limits. If you don't understand even how to really come up with this, you need to go back to solving limits analytically in that section. Take a look at some of those. Alright, and then the next thing we want to do is we want to check f of -1, but f of -1 we said was undefined. So you can see there's a difference between doing the limit, right, finding the limit as x approaches -1, and actually evaluating the function at -1. So this is undefined. Now remember, this had to exist for this to be a candidate of not having any discontinuities. But we can see here that it has a discontinuity because this doesn't exist. So as you can see here, these aren't equal to each other. So we say that it's discontinuous at x equals -1, and not only that, we can give it a name, this discontinuity. It's a removable discontinuity. So where there's a hole in the graph and we're trying to evaluate it at that hole, we say these are removable discontinuities. Let's look at the graph. So this is a graph of our function, and as you can see here, I have a hole at x equals -1. So when you were to graph that function out on a calculator, you would see that it would be just a more or less a straight line. However, this would not be showing up on your calculator.